want to bring something from previous discussion that we maybe unfinished somewhat. One is this picture. So once again, I think I was left you puzzled somewhat. So maybe I have another picture to explain what's happening here. Why is it one room, one person? Okay, so not a bunch of people. Here's the picture that might explain it, unless it's even more confusing. Okay, so the person is on the left, and then this what's in the middle is what's happening. So so the light from the back of the person's head goes around this kind of a round room, and that's how it gets back, and that's how he sees his own back. That if you follow the light, so there is some source of light somewhere, and then off the back of the person's head, the light bounces, makes this round trip, and arrives to his eye, and that's how he sees his back. So that's think about the universe, which might have similar properties, and which actually might easily have those properties. So when you look at the starry sky, and you might think that that might be a star, but actually it might be the sun, and it's light take a trip around the universe and comes back from a different direction. Okay? Makes sense? So so that is just a way to illustrate it. Because why? Because this is a kind of a low-dimensional example of something that is much harder to imagine or visualize when you do it in our three-dimensional world. Okay, so this is some toy example of starting to imagine what could happen if our universe has some complex structure. Not flat like this, what you learn in calculus, but rather maybe curved onto itself. Okay, so all kind of things might happen. So in other words, so the sun sends its light, and then it might take one trip around the sun, or maybe many trips, and maybe every star that we see in the sky, maybe it's the same star. Who knows? Well, we know that it's not the case, but it certainly is conceivable. Okay. Any questions about that? Another issue came up last time is about proving it's about induction, and specifically proving that where is it? Proving the power formula of calculus by using the power formula of calculus. Same formula power. It is not exactly the same. We're progressing from Pn to Pn plus 1. So logically it appears to be all right, but there are branches of logic or views on logic which disallow that, as a matter of fact. Anything that involves infinitely many steps might be disallowed, and that creates complex versions of mathematics. Well, they're complex in the sense that they are not some of the things that we take for granted will not be satisfied. For example, the law of excluded middle, which we use so casually and so many times, might be questioned. What this law means that it is either something is true or not true, and there is nothing else. Okay, and anything that involves infinitely many steps to establish might be questioned either way. So if it takes you infinitely many steps to verify a statement, prove or disprove it, then you don't really know whether it's true or not, which means that a statement could be true, false, and neither. Okay, so then your logic is out of the window, and so that's trouble, obviously. So just a warning. I don't know. We're not going to go in that direction. It is for a number of reasons. It's complex. It is, and it's not exactly mainstream. So we'll stick to this kind of a logic of everybody's logic. Yeah. So we'll be treating infinity as if they do exist. So for example, when we have the reals, line of real, we think of it as if we have, there are infinitely many numbers there, really infinitely many, and we think of it as if we already have it, and we can pick a number anywhere we want. Okay, so it's all in our disposal, at our disposal. Okay, so we're not going to be going deep into logic, but we do go into abstraction with the concepts that we defined previously with set theory, primarily intersections, unions, and the complements of those operations on sets. And now we're taking it to the next level. It is sets exist, but what are the relation between those sets? And those are simply functions. Okay, so functions, a function defined on the set that its domain. Codomain is where the function takes the outputs. That correspondence between two sets. There is nothing else there. So that's the abstraction we're dealing with. So there are no specific nature of these elements of those sets. Those aren't points. Those are numbers, nor vectors, nothing like that. So they're absolutely abstract. Secondly, there are no relations between them either, so there are no distances between them, there are no limits, nothing like that. So it's a purely abstract construct. So the point is obviously to have kind of a bird's eye view of things that you see elsewhere, and see what is that what they have in common. So you have function here, function there. What can you possibly think of that would be equally applicable? And there's plenty of things. Okay, so and one of them is, as we have talked about, is such concepts as functions being one-to-one and onto. Okay, so the image we defined, and I think after I defined it somewhere. Did I define one-to-one onto yesterday? I guess not. Well, so we'll define it when time comes. I went into examples. I think that's what happened, is just going through all the mathematics that you have seen, and seeing examples of functions and how the specifically image will okay, here's the onto functions definition. Surjective function when the image is everything. The whole codomain is the image. Okay, so here are just once again examples of the variety of things that you can encounter in calculus, in particular, in any mathematics, and seeing images, seeing functions, seeing domains, codomains, and seeing images. Okay, so. Just to be in that's calculus 1 is misleading in that way, because all and two functions are all real valued, and the output is also real valued, and that is confusing because of the simplicity. There's so little variety there. Once you go even to calculus 2, already gives you one example that you don't see anywhere else. It's kind of overlooked frequently. Functions in calculus 2. What is a special function in calculus 2 you don't see in calculus 1? A special kind of function. What? No. Integral, either it is definite integral, it gives you a number, or it is indefinite integral, then it gives you gives you another function. So that is another topic for discussion. So let me take the next one. Say integrals. What I meant is actually sequences. Sequences are functions. Okay, so it's what matters is the domain. What is the domain of a sequence? Well, do you remember any sequences? From calculus, what? The domain would be integers, or more likely they're on half of it. So maybe I don't know, typically 1, 2, 3, and so on. Okay, so that would be the typical domain of a sequence. Very different from what you used to in Calculus 1. It's usually the whole real line or some subset of a real line, maybe an interval, maybe um, array, and so on. But now you have an example right away, functions that are very different in nature. So even before you get to Calculus 4, okay? Where that's the previous example is from Calculus 3, where you're talking about either those two examples. Either you talk about parametric curves, and then the domain is a real or subset of real numbers, and the codomain is a two or three-dimensional space, and then functions of two variables. That's the example when the domain is might be within the plane. Okay. So sequence is a good example of what happens with functions that are domain is so sparse. Okay, so and then you can easily figure out, can the sequence as a function be, so this is a sequence, say an is equal to say 1 or n, just to refresh your memory. Then such a function is could be from set, say n. Remember notation for n, natural numbers, to the reals. That's a typical situation about sequences. The inputs are natural numbers and the outputs are reals. Okay. So all of this is an example. Since it was brought up, integrals are interesting. Integrals or derivatives. Just to take it to the next level. Otherwise, so if we cannot use this experience in such a way that we're going to look back at calculus and suddenly see some things that we didn't see before, then it would be a little bit of a waste of this course. So let's take a functional look at things that are not functions as far as calculus is concerned. How about differentiation? Can we look at differentiation as a function? Not derivative, differentiation. Well, as an example, you may have seen, so certainly you've seen this notation. X prime is equal to 2x. But here's another notation. The same thing. Does it look familiar? So, what ddx parentheses, and what's inside the parentheses? A function. Okay. So, well, what is the on the right? 2x. It's also a function. So you take a function, x squared, you do something with it, and then at the end you have another function. Okay. What do you call this? Well, no. What?
Differentiation?
Yeah, it is, but imagine that you don't know what's happening there. I mean, this is a specific example of something, but so that's an example of differentiation, but you can do also anti-differentiation, right? Mm-hmm. And you going the opposite direction, the same story. Once again, function is given to you. Well, maybe it's not given to you, maybe it's given to somebody else, and then that person does something with that function and then gives you back another function, okay? So you don't even know what that person did with a function. What do we call this process? The answer is surprising. We also call it a function. A function of functions. So x squared is the input. 2x is the output. Okay, so you see how we can understand differentiation as a function. So this is a function. It processes functions and produces new functions. So the domain is differentiable functions. The codomain is, say, just functions in general. Okay? Just an idea of once again, looking at an more abstract look at things that you saw in calculus many times. And now you can look at anti-differentiation, which is well, to be discussed, but it's just another example of how we can process functions into functions And then you can do a lot of things like that. But let's just have one example of, once again, differentiation as a function, turning functions into new functions. Okay, so but it's still a function. Just to remember that this is not when we speak of sets, we do not substitute them for some numbers, not even vectors, not even points. They could be very, very different from that. Even within mathematics, interesting examples are outside of mathematics too, but if you just keep studying mathematics, you'll have so many things, and so many of them can be treated as just different kinds of functions. So differentiation, integration, and everything you can think of. On the other hand, you can so let's say, well, here's another example. Integral x squared dx is x cubed over 3, hypothetically. Okay, so it's a similar, a function of functions. So input, output. But there is another example, which is kind of halfway. Integral from from 0 to 1 x squared dx is equal to 1. Once again, the input is a function, but the output this time is a number. So you don't know. You can have anything you can want, from functions to functions, from numbers to functions, from functions to numbers, and vice versa, and all combinations of those. So just examples, so that you do not be over reliant on when it's doing abstract things on narrow a set of examples from calculus. So when we do it abstract, there's a good reason for it, because we just have so many functions that we cannot rely on our intuition or visualization. So image the image. Okay, so it might be complex. You don't know what it looks like, depending very much depending on the circumstances. Okay, so we have functions that are onto. Okay. This is the definition. The function is onto, also known as surjective. Okay, the second one is a matching. You remember how many matching things we have? Intersection and unions, for example. They are matching, going kind of in different directions, but they are side by side. And matching a pair of matching a concept of onto functions is functions that are one-to-one. So f from x to y is called one-to-one or injective. If. So, do you remember the idea?
I thought you said that one-to-one was surjective yesterday.
No, it was onto.
That's onto.
Onto,
surjective.
right.
Okay, gotcha. And then one-to-one injective?
No, I may have used the expression very quickly, saying one-to-one onto. In other words, when you have both, and that might have been confusing. So at this time, let's keep them separate for now, and then we'll put them together. So a one-to-one onto. Remember the concept, the idea, before we define it. One-to-one. So, well, the words are actually it is descriptive. The definition of one-to-one. What does it tell you?
There's one y value for every one x value.
No, that's the definition of a function. There is one y for each x. That's any function. Any function satisfies this. There is only one y for each x. Okay, and now a one-to-one function. There is only one x for each. Not one, but rather, how do we say it? No, that's the first line here. Every function, there is only one y for each x. In fact, exactly one, because we're talking to x in the domain. So if x is in the domain and there are no others, we don't consider, if we have a function, we only concentrate on the domain. The domain is given, so a function is defined for every value of x. So if we pick x from the domain, there must be y. How many? One. That's the definition of a function. Only one y, such as y. And now, indeed, we flip that idea, and rather than, well, we're talking about y equal f of x, obviously, that function. Now, there should be only one x for each y. Well, the tricky part here is that there could be less than one. Because it doesn't have to be onto. So if it's not necessarily onto, then there might be y's that do not have any x's. So they're missing. So you cannot find the counterpart. We're moving backwards from y to x, and sometimes we cannot find an x. Okay, so x to y, but then there might be y, and there's no x. Okay, so nothing. So there is at most one x for each y. So that's what we're trying to say here about one-to-one functions. And that is fine to remember because in words, if you can put them in words, it's helpful. But actually, the definition usually is taken put slightly differently, if for any other reason than just for practice, in the contrapositive way. So there is at most one x for each y. What would be the contrapositive of that? So let's try to state it in the form of with the quantifiers. So as you can see, it's written in the sentence, and the quantifiers are in their own order. What's the first quantifier? I'm trying to rewrite this over here with quantifiers. What's the first quantifier? Well, the definition is, the way we wrote it is a bit confusing, but because it's backwards. Y, we start with y. We are looking for a counterpart for y. We're trying to move backwards from y to x. So we actually have to start reading from right. For each y, that is what we're talking about. For each y, what there is, well, how do you say in a more logical way that there's at most one x? It means that if x is what we're looking for, there are no any other is the same. Okay, so that creates an implication here. So if y is equal to f of x and y equal to f of x, say, prime, then x is equal to x prime. Let's take a careful look at that to make sure that we understand that it is indeed the same statement. Okay, remember that uniqueness idea is hard to express in quantifiers if and that's why it kind of looks longer than what it takes to say. So to say at most one x, that's very quickly. On the other hand, if you want to put it logically, you can actually have to say that like you're saying it in the form of uniqueness. So if x satisfies that equation and there is another, then it is unique. How do we express uniqueness? We say, well, suppose there is another one satisfying the same equation, then it is the same x. Okay? That's what it says. Y is equal to f of x and y is equal to f of x prime, like this. So we're trying to say that this is not the case. This is not the case. So I'm crossing it out. So what is written in the diagram on the right is a function that is not one-to-one. So this one is not one-to-one. Okay, so I cross it out with a red line. Well, let me make that clearer.
Is it not even one-to-one if the x prime and x are the same?
No, no. That's the point. If they are the same, they're okay. If they are the same every single time, then we are okay. Yeah, that's the point. Okay, so I have let's take another look at the picture on the right, and we see what is happening is that we do not want to happen. So then how do we write up what we see, what we don't want to happen? We negate it. So let's take that picture without the crossing, obviously, and try to think of what the negation of this picture would look like. That's another way to approach the idea, understanding functions that are one-to-one. So x goes to y and some other x prime goes to y. How do you negate it? Well, there is and there is. Well, I'm afraid we already did that. We pretty much, this is the negation of that diagram is we already written it. Negation. So you negate, there is an x and there is x prime, so that under f they are both taken to y. Okay, so that's what we do not want to have. Okay, so we negate it how? We say that if that such a thing happens, x and x prime, then x and x prime are equal to each other. Okay, so that's what we have. Let me repeat it here so that it will be clear what we're talking about. Using words this time. For any y, in y, if y is equal to f of x is equal to f of x prime, then x is equal to x prime. For some x prime in x. Okay, so this is the definition. So once again, all it says is that you cannot have that. I want to have these side by side. As I mentioned, these two are matched together, the one-to-one and onto. So let me write carry out the same plan for the onto functions. Onto, what's the objective? So once again, I will go with a diagram, and then I'll try to negate it. So this is not onto. So all the x's go elsewhere. So this is the bad one. So this is my function f, and it takes all the x's in set x somewhere in y, but there is one element that's missing. There is no arrow approaching y. Okay, so the idea is once again to cross it out, because that's what we do not want to happen. We want a function that covers all y. So we look carefully at it and then try to negate it. So how does it start? Same way for any y. So, and then what? We were supposed to demonstrate that, or not demonstrate, but rather state that there is a counterpart for y. So just say it.
For any y, there is an x.
There is an x, yes. There is an x in x such that y is equal to f of x. So it looks a little bit simpler. Okay, so okay, so that's the the two definitions. Actually, probably would be a good exercise to write the negations for both of them. Well, negation for both of them. So instead of trying to make sure that the diagram is not satisfied, instead make sure that it does. Okay, so well, let me just do the latter one. Okay, so if I want to write the negation, well, it is actually not a big deal once it's written in such a plain language and very specific language. With the quantifiers in the right order, even though I did not use the quantifiers, but certainly you can see how it works out. The negation is a really easy job to do. So for any y, there's an x such that y is equal to f of x. How do we negate it? How do we negate for any? There is. Okay, so I'm going there is. There is y and y. Such that, how do we negate there is? For any. So there is a y in y such that for any x in x, what? And then we negate the last statement. So y is not equal to f of x. That's the simplest way to put it. So there is no x that hits y under f. Well, that's the whole negation. So that definitely matches the diagram. Similarly, you can write up the negation over here. Let me try to insert the negation of the one-to-one function here somewhere. Okay. And let me once again negate. Negation for any. Once again, we negate it with what there is. So there is a y and y. Such that, and here we have to be more careful because there is an implication here, if and then. So okay, so well, it takes a little bit more work, or you can just look at the diagram and say, well, what you see there. So there is a y with what? Well, I think it is actually probably, it probably can do it way simpler. Well, just to make it more compact, there are x prime in x with x prime not equal to x such that f of x is equal to f of x prime. That's what the picture says. Let me make it. Make it. Quantifiers are based entirely. Okay, so that's the starting point. There are actually, as abstract as this is, there are theorems about it. But before we do it, let's once again have a few examples to make sure that we got this straight. Examples of functions that are or are not one-to-one and onto. So we already have seen last time examples of functions that are not functions that are not onto. Here's an example: y equals x squared, right? Y equals x squared. If it depends on how you look at the function though. So let me maybe make that clear. That as an example, y equals x squared, is it one-to-one? And the answer is depends, because we didn't say we provided the formula, we didn't provide the domain and the range and the codomain. That depends. So remember, every function is a triple. The domain, codomain, and the relation itself. Okay, so it depends. So even though the function looks like this always, but it depends on where your domain codomain is. So the natural choice, as the function is treated in calculus 1, is to say that domain is R, so the x-axis, and codomain is also R, y-axis, right? Then what? Is it one-to-one? No, not one-to-one, and it's also not onto. Not one-to-one, not onto. So, well, actually, the question was, my question was entirely about onto, because one-to-one actually does not depend on that. So then it's not onto. But if you just reduce the codomain, so domain is R, codomain, how about the positive numbers from 0 to infinity? Then yes, it is. It's onto. So a simple trick, and you have a different situation. Depends on the circumstances. Okay. However, no matter what you do, in either case, it's not one-to-one. Okay. So it doesn't matter. You cannot tweak the domain and codomain without it. Well, I mean, you could actually. Well, it's unfair to put it the way I did, because there are more than just two choices. I only chose the codomain 0 infinity, but think about it, what would stop me from doing -5 infinity? It still works. As far as the formula is concerned, it still works. So anything between 0 and that includes positive numbers, and 0 could serve as the codomain, right? So as long as there is a place for y to go, we're fine. So that's fine, and none of these will be still one-to-one. Okay. However, what about well, can you make it one-to-one?
X cubed?
No, I want to take the same function. X squared, can I make it one-to-one? Change the domain, that's right. So do you remember that happening? How the function was not one-to-one and you made it one-to-one? Sine defined on the whole real line, okay, and it goes ups and downs, so it's not one-to-one. And then at some point we said, well, we actually need the arc sine. How do you have arc sine, which is the inverse, without the unless it's one-to-one? So that's the next topic, and then you change the domain. So same story here. If you want to, for example, if you want the inverse, then you cut the domain. So I take the domain 0 infinity, and it doesn't matter what codomain is. It could be R still, and then it's one-to-one. It becomes one-to-one because essentially I cut out half of the graph, half of the function is cut out. So then this is my domain. Okay, and then altogether, especially, so if this is domain, under ideal circumstances is in fact, ideal circumstances is when the domain is 0 infinity and the codomain is 2. Okay, so then I'm left with this and nothing, but I have only positive x's, positive y's. Okay, x, y. The graph is still the same, and there is nothing else. So then this one, unlike the two examples that we just saw previously, this is both one-to-one and onto. Right? So it's still the same relation, but the choice of the domain and codomain allowed us to have a function that both one-to-one and onto, and this is what we call bijection, or we just say one-to-one onto. Yeah, I think I mentioned before. So one-to-one onto is also known as a bijection, and once again back to that point I was making. Why we care about bijections, one-to-one onto, because these are what kind of functions? They have inverses. So it has the inverse. None of the others has the inverse, because you have to simultaneously have what? You're building a new function by reversing x and y, so you should be able to find, when you remember that rule becomes so important, that you cannot have two arrows coming together. Why? Because when you reverse, you do not want to have two arrows starting from the same point. That's not a function anymore, right, to begin with. And secondly, that's the second property. Why the second diagram is bad, because I'm trying to start a function at y, and there is no arrow for y. So in either case, we need both of them in order to build the inverse. Okay, and so once again, it has nothing to do with the idea of inverse in Calculus 1, which is kind of primarily about solving an equation. Well, so an equation will be doing graphs, but really the idea is totally abstract. It is, in fact, well, we'll get to that later. We'll get to inverses later. Let's deal with these a little bit, one-to-one and onto. So we had examples. So we had this one example, y equals x squared, provides us with example both one-to-one and onto. Not one-to-one and onto as well. So let's take another look at these. So functions that are not one-to-one and onto. See here, over here, from Calculus 3, a parameter curve that is a curve in the space on the plane that it cannot possibly cover everything. Okay, so it does not, definitely not onto. On the other hand, it could hypothetically cross itself, which means what? Parametric curve crosses itself. What does it tell you about this curve as a function? It's not one-to-one, right? So it means that there are two different values of input t that give you the same output. So that red dot over there, it's like you're taking a trip. So this is time, r is time. You're taking a trip along a certain road, and then you visit a certain point twice. So that makes it not one-to-one. It's also not onto. So it is typical for a function to be neither one nor the other in calculus, because the difference between the domain and codomain sometimes very significant. So r versus r squared is very much, well, let's just say there are different weights. If you flip it and go instead of from r to r2, so once again thinking calculus 3 over here, we're talking about functions of two variables. So now the domain is big and the codomain is little. Okay, so the graph is typically a surface, and then think about it. Think about this function being onto. It could be, doesn't have to be, but could be easily. Why? Because once again, the surface. If I know the surface, how do I find? Remember how you find. If you know the graph, that surface on the right, how do I find the image? Projection on what? No, that's the domain. Projection on the domain gives you all possible values of x that are available, right? So if there's a point there somewhere, that means that there's an x and y or rather xy here, and a point z over there. And so when you go down, it means that that point on the xy plane is in the domain. But I'm talking about the range or the image. You project it horizontally on the z-axis. Okay, so like this. So if this is your z-axis, you take all of this and do it like this. There will be a lot of points, obviously. Every single point on the surface is taken horizontally towards the z-axis. Okay, and combination of all of those z's will give you the output, and that will be typically. You can imagine that it will be. You already can see that it's probably is going to be an interval, and probably there will be many. It will be not one-to-one, right? So you can see every time you have something like this, what does it tell you? If the graph has this, what?
Maximum?
No, not what I have in mind.
It's coming back through
Yeah.
points that have already been passed. Like,
It comes back, yes. So from this level comes to that level, same level.
It's not one-to-one.
It's not one-to-one. So the two different x's, same y. So that's not one-to-one. So that function already you can tell right away that this one is not one-to-one. This one. Okay, since we are doing I did this example of integrals, differentiation. Let's say differentiation, d dx from, well, what's the domain? Well, what function do we differentiate? No, well, I want all of them. Well, there's a word for it. Function that we are able to differentiate, known as? No.
Differentiable?
Differentiable. Yes, differentiable. So differentiable functions then is the domain. It's a bit trickier. What is the codomain? Well, we cannot say differentiable because a derivative of a differential function is not necessarily differentiable. So we'll just say functions. Anyway, so to wrap it up, is it one-to-one? Why not?
Not necessarily.
You could have two differentiable functions that like differentiate and have the same.
Yeah, two functions have the same derivative, right? So yeah, so x and x plus 1 on the differentiation give you the same function.